This is the 34th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. In this video, we introduce MIPS assembly and the Mars MIPS simulator. To write and execute MIPS assembly, we'll be using a program called Mars. Mars is both an IDE for writing MIPS assembly and a MIPS simulator. The simulator is what allows you to run your MIPS code on non-MIPS hardware. Mars is free and you can download it from Ken Vollmar's website at Missouri State University. So if you're looking for Mars, the easiest way to find it is to do a Google search for MIPS Mars, and the Mars website will almost certainly be the first one that comes up. Mars is written in Java, so downloading it is just a matter of downloading and running a jar file. Although Mars is hosted by Ken Vollmar's website, most of this code was actually written by Pete Sanderson, who recently retired from Oberlin College. The first thing you'll do when you launch Mars is either open or create a new file. So in this case, we'll create a new file, and when you do that, you end up with an editor window that you can type some assembly in. So to get started, let's type a simple program. The first thing you want to do is type the text directive. This tells the assembler where your code begins. In future videos, we'll see some things that get put above this text line, but for now, just get in the habit of adding it. And so now let's add a few simple assembly commands, such as add I, T0, 0, 6, add I, T1, 0, 7, and add T2, T0, T1. Off to the right, you'll see a list of registers. Notice that each register has both a name and a number. You can use either in your assembly code, but in most cases, it's easiest to use the names, like I did here. These registers all have a conventional use, so when you use the name instead of the number, it's easier to remember what you're using the register for. When your program is complete, you need to save it. So I'll just accept the default name here. And when you do that, the wrench and screwdriver button is enabled. This is what you push when you want to assemble your code. So when I push the button, you see the view switches to the assembled view of the code. And this has several columns. From right to left, you see first the source column here on the right. That's the code as you've typed it in. And then one step over to the left is the column labeled basic. This is just a slightly different view of the assembly code. This is where Mars has translated it so it looks a little closer to the hardware. For example, the constant value 6 is expanded out into 16 bits, and the register names are replaced with their corresponding register numbers, because it's of course the numbers that get put into the machine code and run through the hardware. The next column is the code. This is the actual machine code written in hexadecimal as opposed to binary. If you translated this hexadecimal into binary, you would see something very similar to the examples we went through earlier in the video. And then there's the address column. This address tells you where the code will be in RAM. Now remember that each machine instruction is exactly 32 bits long. 32 bits is 4 bytes, so notice that the sequence of addresses increase by 4. Now you can run your code by using either of the buttons next to the assemble button. They both have a green circle with an arrow in them. This first one runs the program to completion. The second one with the little 1 in the lower right corner runs one line of code at a time. So if I click this button, you can see that the first line of assembly was executed, which added 6 plus 0 and put the result in T0. So now you can see that T0 contains the value 6. Similarly, if I take the next step, T1 contains the value 7. And if I click this a third time, it will add T0 and T1 and put 13, which is D in hexadecimal, into register T2. The first challenge you'll run across when writing assembly is breaking code down into smaller machine-level steps. For example, suppose you wanted to add 3 numbers. In Java, you might write something like this: x equals y plus z plus w. However, suppose that Java only allowed you to perform one addition per statement. In that case, you'd have to divide the expression into 2 or more lines of code, perhaps like this. This is precisely the situation we face when writing assembly. The hardware can only add 2 values at one time, so to add y, z, and w together, we need multiple assembly statements. If we assume the variables x, y, z, and w are stored in registers T0 through T3 respectively, then our assembly code might look something like this. So this process of breaking your Java code into smaller chunks and then running it in a simulator like Mars is the basics of assembly. There's of course a lot more to learn, but this will get you started. To better help you write your first few assembly programs, let me go through the conventional uses of the registers. Mechanically, registers 1 through 31 are identical. Technically speaking, any of these registers can be used for any purpose. That's why they're called general purpose registers. However, there are conventions for how each register is used. Following these conventions makes it easier for code written by different programmers to work correctly together. Let's begin with register 0, conveniently named 0. This register is hardwired to always contain the value 0. It can't be changed. As we learn more assembly, we'll see several examples of where it's helpful to have a register known to contain 0. In fact, we've already seen the first example. We loaded an immediate value into a register by adding that immediate value to 0. This approach relies on the fact that register 0 contains 0. AT stands for Assembler Temporary. This register is reserved by the assembler. We'll see examples of how it's used when we cover pseudo instructions. By convention, a function's return value is placed in V0. And function parameters are placed in registers A0 through A3. We'll see examples of this in the next video where I talk about our testing framework. The temporary or T registers are your main workspace. For the most part, these are the registers you'll use to store variables and other temporary data. The saved or S registers are used to protect data when you call a function. We'll say a lot more about that in the video on functions. K0 and K1 are used by the kernel, which is part of the operating system. We won't do much with that in this course. GP, FP, and SP all point to commonly used parts of RAM. We'll talk about those in the video on load and store instructions. And finally, the RA register stores the return address. When you call a function, the computer needs to remember what line of code to return to when the function's finished. The RA register is what stores that value. Now, like I said, there's a lot more to learn about assembly, but this video should give you just enough information to write some simple assembly code and experiment with Mars. Have fun!